Welcome back, Focus Learners. I am absolutely thrilled to have you here for today's explainer. We are diving deep into something that's literally changing how artificial intelligence operates from the ground up: the architecture of AI memory and Retrieval-Augmented Generation, or RAG. If you've ever wondered how an AI evolves from just a basic text predictor into an agent that actually learns and retains complex information, well, you're in exactly the right place.
But first, let's start with a frustration I know we've all experienced. You know the feeling, right? You're interacting with an AI agent, and it handles the first 3 or 4 messages perfectly. It pulls up your order, confirms your name, updates a quick detail, but by message 5, total amnesia. It completely loses the context, confidently hallucinates a totally wrong answer, and your token costs just shoot through the roof. It's incredibly frustrating, and honestly, this perfectly sets up the fundamental problem we're tackling today: how models process, or entirely fail to process, memory at scale.
Okay, let's dive into this. Here is our roadmap for today. 1. Why AI agents forget. 2. Embeddings and basic RAG. 3. Why basic RAG fails. 4. Hybrid search and graph RAG. 5. Active dreaming consolidation. And 6. Building production pipelines. Section 1. Why AI agents forget. The limits of working memory.
So, an LLM's working memory is strictly limited by its active context window. It's incredibly fast, for sure, but it is entirely temporary. Think of it kind of like a computer's RAM. You can't just stuff thousands and thousands of tokens into an LLM and expect it to hold on to everything forever. Eventually, you hit context overflow, and when that happens, the state just vanishes. Poof, gone. What we desperately need is a system that doesn't just jam data into a prompt, but actually tracks the difference between episodic memory, meaning what just happened, and semantic memory, meaning what is universally true.
Section 2. Embeddings and basic RAG. The baseline fix. When that context window just isn't enough, we have to give the AI an external brain. And this is exactly where Retrieval-Augmented Generation, or RAG, enters the picture. Standard RAG enhances an LLM by taking external documents, chopping them into manageable chunks, and indexing them. Then, when you ask a question, the system retrieves the most relevant chunks based on semantic similarity and augments the LLM's prompt with that historical context. It relies heavily on dense vector representations and cosine similarity to find exactly what it needs. Under the hood, this process is pretty wild. Raw text is ingested and chopped into specific token IDs by a dictionary. Then, an embedding layer mathematically projects those tokens into a dense vector space, very often at 384 dimensions. It literally transforms human language into spatial mathematics. This is what allows the database to rapidly compute how close or similar two pieces of text are to one another. Section 3. Why basic RAG fails. The scaling problem. Now, basic RAG works wonderfully for simple, one-shot queries. But when you deploy it in long-running agentic workflows, flat vector storage catastrophically breaks down. It's absolutely crucial to understand these 4 specific failure modes. First up, context poisoning. If an agent hallucinates, that error gets saved right back to the database. Next time, it retrieves its own error, reinforcing the hallucination in a really dangerous feedback loop. Second, context distraction. Semantic similarity does not equal relevance. Retrieving 10 broadly similar but totally irrelevant conversations just dilutes the AI's attention with noise. Third, context clash. Say the AI pulls up both the user's old address and their new address at the exact same time. Now it has to guess which one is true, and that's a coin toss you definitely want your AI making. And finally, work duplication. This is when multiple agents query and process the exact same data because they lack a shared state, creating massive computational waste. To solve this mess, we have to move away from flat databases that just perform exhaustive, fuzzy searches. Instead, hierarchical memory architectures, like MemGPT for example, treat memory like a computer operating system. It dynamically pages data back and forth between a tiny, lightning-fast core memory and a massive external archive. By explicitly routing information, rather than just fuzzily matching it, these hierarchical systems can save an astonishing 85 to 95% on token costs. That is a real game changer. Section 4. Hybrid search and graph RAG. Solving for precision. But saving tokens is only half the battle, right? We also need pinpoint accuracy. When we compare retrieval mechanisms, the math is pretty striking. Dense-only retrieval casts a wide, fuzzy net, hitting about 60% precision. Symbolic filtering gives you hard boundaries. But hybrid retrieval, that's where the magic happens. By combining dense vector ranking, which requires a cosine similarity greater than 0.7, with discrete symbolic filtering, the system achieves a massive leap up to 95% precision. Let me give you a vital analogy to show why this matters so much, especially in high-stakes environments like medicine. If you use a basic vector search for a patient with high blood pressure, it might just find the phrase, "Drug X treats hypertension." That is semantically true, but it's dangerously fuzzy. GraphRag, on the other hand, enforces exact multi-hop reasoning. It traverses a web of knowledge to realize, wait a minute, patient A takes drug Z, and drug Z has a lethal interaction with drug X. Therefore, do not prescribe drug X. See the difference? Vectors give you proximity. Knowledge graphs give you verifiable relationships. So how do we actually build this? Here is the standard GraphRag extract, transform, load pipeline. Step 1. An LLM reads unstructured text and extracts distant entities and relationships. Step 2. And please remember this, it's a critical rule. A validation layer strictly checks those extractions against predefined database schemas. You absolutely must use fixed predefined queries here. If you let the LLM hallucinate database queries, you will corrupt your entire graph. Literally the whole shebang. Finally, step 3. The agent queries the clean graph via multi-hop cipher traversals to answer those complex questions. Section 5. Active dreaming consolidation. Biologically inspired memory.
This is fascinating. Just like the mammalian hippocampus consolidates memories during sleep, we can design AI agents to do the exact same thing. During an offline sleep phase, the agent looks back at its recent execution failures. First, it uses an algorithm to cluster similar errors together. Then, it uses an LLM to abstract those clustered failures into a candidate role. Essentially, it's learning a lesson. Finally, it tests that new role by generating simulated, counterfactual scenarios. If the role works in the simulation, boom, it becomes a permanent memory.
This active dreaming completely changes the geometry of AI memory storage. Without it, raw episodic memory, literally every single thing the agent ever did, grows linearly. It gets massive, bulky, and incredibly slow. But through consolidation, the agent actively converts those bulky traces into a highly compressed, strategic repository of semantic facts. It turns a linear pile of data into a logarithmically growing library of verified generalizable knowledge. Section 6. Building production pipelines, making the trade-offs. In the real world, engineering is all about making the right choices. When deciding on an architecture, it always comes down to latency, fidelity, and cost. If you need answers fast, like under 50 milliseconds, and your costs need to stay low, VectorRag is your tool. But you have to accept that the fidelity will be slightly fuzzy. On the flip side, if you need exact, explainable multi-hop reasoning, you need GraphRag, but you'll pay for it with slower latencies and infrastructure costs that are 1.5 to 2 times higher. The absolute best production systems, they use hybrid orchestration. They route the simple questions to the vector database, and they save the expensive graph traversals for high-stakes, complex reasoning. And that leaves us with a final, pretty provocative question to think about. When you're building your next agent, ask yourself, is your AI's memory actually a structured, strategic resource? Or are you just dumping tokens into a flat vector database and hoping for the best? Because true agentic AI requires true agentic memory. Thanks so much for learning with me today, and I'll catch you on the next explainer.